Hello everyone, welcome to the YouTube channel of Lightway Research and Technology Center. In this video, I'll show you how to estimate ordinary least squares regression in Eviews. I'll show you everything you need to do before you can proceed with OLS estimation in Eviews. Please, if you are just coming across our channel for the first time, kindly subscribe to this channel by clicking the subscribe button below, and also turn on your notification bell so that you can be informed when we release new videos on our channel. Here are what we are going to look at in this particular video. The first thing is model specification. Next is descriptive statistics, followed by multicollinearity test, unit root test, OLS estimation, which is the due in this particular video, then interpretation of OLS results, and the last part is post estimation test. After you must have developed your objectives, research question, as well as your hypothesis statement, the next most important thing is model specification. And your model specification, you are going to distinguish between dependent and the independent variables. Here we have two models. The first one is the functional model, while the second one is the econometric model. The only thing that distinguished, or the things that distinguish the first model from the second one are the beta or the intercept. Next is the error time. So this error times makes it econometric model. If you look at the first model, you will notice that we have two independent variables. What are independent variables? X1 and S2 are the independent variables here. Y is a dependent variable. So this model means y is a function of x1 and x2, where y is the dependent variable and x1 as well as s2 are the independent variables. Now, the econometric model has the lane, which is the natural logarithm. Most times we transform our data to address or to avoid the problem of heteroscedasticity. So here we have the dependent variable, which is a transformed variable, and the independent variables are also a transformed variable. So this is a log-log model. And another advantage of this type of model is that it makes it very easy to interpret the results, because you can easily say that a 1% increase in the independent variable will lead to so percent increase in the dependent variable. Beta naught here is the intercepts, which we can also reverse to as constants, while beta 1 and beta 2 are the parameters. This beta 1 denotes the magnitudes or the coefficients of x1, while beta 2 is the magnitude or coefficients of or parameter of x2. This is the error time. And why do we need to put this? You see, most times when you have a model like this, in fact always, in all cases, it is impossible for these two variables to explain all the variations, that is the 100% variation in y. Whenever you have a model and your independent variable explains 100% variation in y, that means there is a problem of multicollinearity in that particular situation. So here, let us assume that s1 and s2 explain 70% of the variation in y, then the remaining one, that is 30%, will be captured by this error time. So here we have one dependent variable, y, and two independent variables, x1 and x2. Now, once you have your model, the next thing is the descriptive statistics. This particular uh, test enables you to determine the behavior of your data. It provides the mean, the median, the maximums, the minimum, the standard deviation, the Jarque-Bera, as well as the probability. So, if you want to know more about descriptive statistics, please go through our channel. We have already released video on how to do descriptive statistics in Eviews and how to interpret the results. Kindly check our channel for a video on descriptive statistics. But in this particular video, I'll show you how to run descriptive statistics, but I will not explain it because we have already done that in one of our previous videos. The next thing is the correlation matrix, which enable us to know whether our model is free from the problem of multicollinearity or not. Also, we have released video on how to check for the problem of multicollinearity in any model. In fact, we discussed two major tests. The first is the correlation matrix, and the second is the variance inflation factor, VIF. Please check our channel for videos on multicollinearity test as well. But in this video, I will also show you how to perform multicollinearity, but I will not explain the results or how to address the problem because we have already done that in one of our videos. Next is the unit root test. We have different tests to perform or to check whether a variable is stationary or not. One is augmented decay-Fuller, followed by Philip-Ferron, followed by Kwiatkowski-Philip-Mission test, and we have NG-Perron and some other ones as well. Also, we have done video on how to check for unit root. Please take a look at our channels, all the videos. We see videos on yes, we have two videos on how to perform stationarity test. Then the second one explains how to make use of all unit roots adding, that is the shortcut and the long cuts, and we provide a clear explanation of how to do all those tests. Please check our channel for that particular video as well. But we'll take you through the null hypothesis, the alternative hypothesis, as well as the decision rule in this particular video, because before you can estimate an OLS regression, you must know whether the variable is stationary at level or not. One of the conditions of OLS estimation is that all the variables must be stationary at level. You cannot make use of OLS regression for a variable that is I1, that is stationary after first difference. So you need to first check for the unit roots and ensure that your variable is stationary at level. And the known hypothesis, particularly for augmented decay-Fuller test, is that the series has a unit root. That is, the series is not stationary. And the alternative hypothesis is that the series does not have a unit root. In other words, the series is stationary. And the decision rule is very simple and straightforward. Reject the known hypothesis, that is, the series is not stationary, and conclude that the series is stationary if the absolute value, please take note of the word absolutes, of ADF test statistics exceeds the critical value at 1%, 5%, or 10%. Take note that 5% is the confessional level, so I always advise that people should stick to 5%. Or if the probability value is below 1%, 5%, and 10%. Otherwise, fails to reject known hypothesis and conclude that the series is not stationary. So this is the decision rule. First, talks about the critical values, and here we are talking about the probability value. But the best way is just to look at the probability value. If it is below 5%, then you know that such variable is stationary. Now, let us look at OLS estimation. Please, I will take you through the theory before showing you how to do the estimation in Eviews. We have three ways of specifying our equation in the Eviews environment. The first is that you can just say y, that is the dependent variable, followed by constants, which is c, then followed by the independent variables. And the second way that you can use, the second method is y, x1, x2, and instead of placing constants immediately after y, you can move it to the front. This third one is not common. This is an estimation without constants, so it is very rare. So when you want to estimate OLS, please make use of the first one or the second one. But if you have a strong reason of estimating OLS without a constant, then you can make use of the third method. Now, let us quickly look at the interpretation of OLS results. Please take note that the general principles of interpreting linear regression model with a continuous dependent variable as this. The first thing you need to take note is that we have three x. The first x stands for sign, the second one stands for size, and the third stands for significance of coefficients. Then another result that we get, or the statistic, is the statistical fitness of the model, and this is revealed by R square and adjusted R square, as well as F statistics. So these three statistics indicates the fitness of our model. R square is different from adjusted R square. Please take note of that. I will explain the difference later. Another statistics that you will get is the Ramsey test. This particular one is used to check for the presence of first order serial correlation. Of course, we have also done a release video on how to check for serial correlation, as well as how to address it in Eviews. You can check our channel, you will see one of our videos that deals with that. But the only difference is that in that video we don't really explain in depth this particular one sentence. The reason is that it comes along with OLS results, so I will make sure I do that in this particular video. Next statistic we get is the information criterion, and this one is used to select the best model. In a situation whereby you have 2-3 models, the tools that you can use to select the one that gives the best results is this information criteria. But when you have just one model, you don't really need this. You don't need to report it. It is only useful when you have 2 or more models. Then you compare the information criterion, then from there you choose the model that produce the best results. Now let us quickly take a look at the interpretation of results designed, that is the first X. The sign can either be positive or negative. That is, when you have your OLS results, the magnitude of the dependent variable will carry either minus or positive or plus. When it is positive, that's minus, and when it gives you negative, that is what? When it gives you negative, that's minus. When it gives you plus, that is positive. And what does positive signs mean? It means that there is a direct relationship between the dependent variable and that particular independent variable. Take note that when I was explaining the model specification, I made it clear that when you take the natural log of your variables, it is the interpretation of your result. So because it converts the variables to percentage, the data, it converts us to percentage, and with that you will be able to say that a 1% increase, for instance now, if the relationship between x1 and y is positive, then you can say a 1% increase in x1 leads to so percent increase, that is excess percent increase in y, which is the dependent variable. But if the relationship, if x1 carries negative, that is minus, then it means that an increase in s1 leads to a decrease in y. That is inverse relationship. So when you have your OLS results and you notice that x1 has minus, then you should know that an increase in x1 will lead to a decrease in the dependent variable. So this, the magnitude, the rate at which the decrease will occur will now be indicated by the what? By the size. That is the second x. So now let us look at the size. The size reveals the magnitude of the impact of dependent variable on the independent variables. So when you have your OLS results, the coefficients there is what? Is the size. While the sign is the one that shows whether the relationship is direct or inverse. So the size can also be reversed to as magnitude. So you can say, in other words, the size measures the magnitude of variation in the dependent variable as a result of the change in the independent variable. So when you have your OLS results, the first thing you have to look at is the sign, next is the size, and the last is the significance. And why do you need to look at significance? When you are stating your hypothesis, you will notice that what is written there is that there is no significant relationship between the dependent variable and the independent variable. For instance, if we are looking at the impacts of carbon dioxide emission on mortality rates, the non-hypothesis will be there is no significant relationship between what? Carbon dioxide emission and mortality rates, because mortality rates will be dependent variable, carbon dioxide emission is independent. So there is no relationship between the mortality rates and carbon dioxide emission. And what tells you whether the relationship is significant or not is what? Is the last x, which is significance. And look at the alternative. There is a significant relationship between the dependent and the independent variable. In the case of mortality rates and carbon dioxide emission, now you will have there is a significant relationship between mortality rates and carbon dioxide emission. That's what you will put there if you are looking at the relationship or the impact of carbon dioxide emission on mortality rates. So now, when the probability value of carbon dioxide emission is less than 5%, that means it is significant. So you can now say that there is a significant relationship between mortality rates and carbon dioxide emission at 5% level of significance. So the reason why we look at the type else is because of the hypothesis, because it is directly related to the hypothesis. So now, when you are looking at the significance, the statistical significance, then you have this decision rule. Reject the non-hypothesis if the probability value is less than or equals to the chosen level of significance. That level of significance will be determined either by you, by your supervisor, by the journal editor, or by your institute. For instance, now in social science, we use 5%, 10%, while in pure science, they prefer 1%. Now, if you notice that the probability value is less than 5% but greater than 1%, then you say the relationship is significant at 5%. But if it is less than 1%, it means it is significant at 1%. Also, if the probability value of the independent variable is greater than 5% but less than or equal to 10%, then you can say that the relationship is significant at 10%. So here is the decision rule. Reject the null hypothesis if the p-value is less than or equals to the chosen level of significance and concludes that the independent variable has a significant impact on the dependent variable. Otherwise, fails to reject the null hypothesis and conclude that the independent variable has no significant impact on the independent variable. So, in a situation whereby the probability value of the independent variable is greater than 10%, that means there is no significant relationship. So, you cannot reject the null hypothesis. But if the p-value is greater than 5% and less than 10% or less than 5%, that means there is a significant relation. So in such case, you must reject the null hypothesis and go with the alternative hypothesis. Now this is just a summary of everything I've been saying about statistical significance. You can see the p-value, the significance level. If the p-value is less than or equals to 0.01, that means it is significant at 1%. If it is less than or equal to 0.05, that means it is significant at 5%. And if it is less than or equals to 0.1, it means that it is significant at 10%. But take note, the conventional level is the 5%. So I would suggest that you should always stick to that. Now the next thing we need to look at is the statistical fitness of the model. Please take note that three key indicators of statistical fitness are R-square, adjusted R-square, and F-statistics. The only difference between R-square and adjusted R-square is that when a new variable, a new independent variable, is added to a model, R-square will always increase, irrespective of the fact that the variable add value to the model or not. But adjusted R-square will only increase if the variable contributes to the model. That is, if it is useful in explaining the dependent variable. If a particular independent variable is not useful in explaining the dependent variable, adjusted R-square will not increase, but R-square will always increase. So that's why most times we always rely on the adjusted R-square to determine the statistical fitness of a model. For F-statistics, it tells us whether the independent variables, that is all the independent variables S1 and S2, are significant in explaining the dependent variable. Take note, T-statistics shows whether an independent variable is significant in explaining the dependent variable. But F-statistics shows that whether all the dependent variables are significant or not. So the condition is that if the F-statistics is less than, that is the probability of F-statistics is less than 5%, it means that the variables, the independent variables, are significant in explaining the changes in the dependent variable. And in such case, we say that the statistical model as a good fit. And with respect to adjusted R-square, once you have anything above 50%, that is 0.5, you are okay. Take notes, when the R-square or adjusted R-square is equals to 1, it shows that your model is not good. It means that your model is suffering from the problem of multicollinearity, so you need to address that. But when you have value of adjusted R-square standing at 0.9698, your model is perfect. So please, you need to watch out for the value of R-square, adjusted R-square, as well as F statistics. Here is everything I've said about those two statistics. You can see R-square, adjusted R-square. Measure the proportion of the variation in the dependent variable accounted for by the independent variable in the model. So for instance, if adjusted R-square is 0.98, it simply means that the independent variable explains 98% of the variation in the dependent variable. Now the remaining 2% is explained by the error time. So the value ranges from 0 to 1, where 0 means that the independent variable do not explain any variation in the independent variable. That is a very rare case, but you can have 0.00 something. Thus, the closer adjusted R-square is to 1, or R-square if you want to make use of R-square, the more the model is a good representative or representation of the data and therefore a good fit. So it is better if the adjusted R-square or R-square is closer to 1, but it must not be equals to 1. Now, the closer the R-square is to 0, the more the model is a poor fit. So it must not be 0, and it must not be too close to 0. When it is too close to 0, it simply means that your independent variable are not relevant. So you need to look at the key, you need to look out for the key independent variable, then you incorporate those ones in your model. Please take notes, in case you have 2 or more models and you want to compare the model based on the value of the R-square or adjusted R-square, you must ensure that the sample size of the 2 models are equal. Also, the dependent variable must be the same. If the sample size are not equal and the dependent variable are not the same, you can't compare that, because you will certainly have different results. But when you have those 2 things in place, then you can proceed with the comparison. Now for the statistical, for the F statistics, it tells the overall significance of all the variables in the model, which I've already said. The decision rule is this: reject the null hypothesis, which is here, that is beta 1, beta 2, up to the last beta equals to 0. Reject the null hypothesis if the p-value of the F statistics is less than 5%, you know, I've already mentioned that, and concludes that all the variables in the model are jointly significant. But if the p-value is greater than 5%, you should know what to do. Now let us quickly look at the Dub-Watson statistics. For Dub-Watson statistics, we have our value range from 0 to 4. That is the value of Dub-Watson statistics. It ranges from 0 to 4. When the value of the Dub-Watson is between 1.5 and 2.5, it means that your model is free from the problem of serial correlation. So in that case, you don't need to worry about the outcome of your model. But when the value ranges from 0 to 1.44, then you should be worried about was the problem of positive autocorrelation, and when the value exceeds 2.55, then there is a problem of what? There is a problem of negative autocorrelation. So you should take steps to address that particular problem. And in one of our videos, particularly the one on serial correlation, we provided solutions, or we explain how to address this particular problem. Is just by adding the lag of the dependent variable. Of course, you can also increase the sample size if it's going to address the problem, but one of the major ways is just to add the lag, the first lag of the dependent variable. Now, what is the non-hypothesis for advancing statistics? The non-hypothesis: residuals are not autocorrelated, alternate residuals are autocorrelated, and the decision rule is just straightforward. If the value of dw is between 1.5 and 2.5, then there is no problem of serial correlation. But if it is greater, that means you cannot do what? You have to, when the value is greater than 2.5, that means there is a problem of serial correlation. That is, the residuals are autocorrelated. In such case, you have to reject the non-hypothesis. But when the value is between 1.5 and 2.5, then there is no problem. There is no problem of serial correlation. That is, the residuals are not autocorrelated. So in such case, you cannot reject the non-hypothesis. Now, for the information criteria, please take note that this particular indicator is only useful when you have two or more models. So when you have two or more models and you want to compare which one is the best, then you can rely on the information criterion. And we have different methods that you can rely on. The first one is AIC, SIC, HQ, FPE, and LR. So you can make use of any of these methods. But what you need to check for is that any model that is criterion model that gives you the smallest information criterion, it means that model is what? Is the best. The best model is the one with the smallest information criterion values, and such model neither underfits nor overfits your data set. So the model with the least information criterion value is what? Is the best. So if you want to compare 2-3 models now, then you have justification for using SIC. Then you take a look at the SIC of all the models. Then you pick the one that has the lowest SIC. For instance, if we have model A, B, and C, and for model A the SIC is 2, for model B the SIC is 1, and for model C the SIC is 5. You can, if you look at it, the model B give us the least, the smallest value, which is 1. So it is the best. That's just it. Is very straightforward. But when you have just one model, you don't need to care about the interpretation of information criterion. So now, once you have your OLS results, you also need to check whether the result is reliable or not, whether the estimates are efficient. If you need to check out whether those results are valid, that is, they are in line with the post-estimation test. The first thing you need to look at is the Ramsey reset test, and this particular one tells you whether the model is truly linear or not. And we have also done a video on how to perform Ramsey reset test in Eviews. Please check our channel. We've provided a clear explanation of the results and what you need to do when you have issues with it. The next is normality test. This one also we have covered it in one of our previous videos. Please just take a look at our channel, then you see a video on how to perform Jarque-Bera normality test in Eviews. The next one is the serial correlation, which is similar to the Duckworth, but this particular one has a statistics or a test that makes it more unique. We have also done a video on it, and we'll also explain the difference between this and the other one, DW, in that particular video. Please take a look at our channel and get that video. That video is actually part of this particular video as well, because this video explains ordinary least square from A to Z. So those videos, and if you also check the description of this particular video, you will see the link to all of these post and pre-estimation tests. And the next, which is the last here, is the heteroscedasticity test. This particular one also, we have covered it in one of our previous videos. Please check our channel for videos on how to perform heteroscedasticity test in Eviews. So now I will take you through how to do all these pre and post estimation tests in Eviews, and also how to estimate OLS regression and interpret the results. Okay, this is my work file, and here you can see that I've already transformed all the variables. This is the dependent variable, which is the natural log of the manufacturing value added. The first independent variable here is capital, the natural log of capital. The second is unemployment, which people often refer to as labor, and this is the natural log of unemployment. And the last here is exchange rates, which is also the natural log of exchange rate. In case you want to know why we take the natural log, or take the natural log of these variables, you can check our previous video. But briefly, the first reason is that all these variables are not in percentage. They are in billions. So since they are not in percentage, it is legal, it is valid to take the natural log of all the variables. But if any of them is in percentage, it is only those ones that are not in percentage that you just take natural log, then you make use of the one in percentage raw. And another reason is that when you take the natural log of all your variable, you address the problem of heteroscedasticity partially. You understand what I'm saying? So it is always good to take the natural log of your variable. Now the first thing that we are going to do is descriptive statistics. I will just show you how to run it, no explanation, or the post and pre-test, because we have already done that in our previous videos. So now to check for the descriptive statistics, you can go to quick, then you select group statistics, then descriptive statistics. You can pick common if your observations are equal, then common, you have this window. Here now you will now need to enter the variables one after the other. But I don't like this method, so the best is to highlight the variables there. The first thing is you click on the dependent variable. Once you click on the dependent variable, then you press your control, then you select the independent variable one after the other, then the second independent variable, the third independent variable. So once you are done with that, then you go to quick. From quick you move to group statistics, descriptives. If all the observations are equal, then you click common. You can see all the variables appears automatically, then you click OK. So this is your descriptive statistics. This is your descriptive statistics. The explanation, if you want to know more about it, please check our channel for videos on how to perform descriptive statistics in Eviews. The next thing is multicollinearity test. So here we are going to make use of correlation matrix, but please take notes. If you want to know more about it too, about correlation matrix as well as variance inflation factor, check our channel for videos on how to perform multicollinearity test in Eviews. So now, once you highlight all the variables, you go back to quick. Once you get to quick, you select group statistics. Then instead of descriptive statistics, you now select correlation. Once you click on this, you will have this window with list of the variables selected here. Then you click OK, you have your results. So this is your correlation matrix. The next thing we need to do now is to check for the unit roots of all the variables. Please take notes. Before you can make use of OLS regression estimates, OLS method, all your variables must be stationary at level. If one of your variables are not stationary at level, then you have to make use of other methods like ARDL and so on and so forth. But for you to make use of OLS method, you must ensure that all your variables are I0, that is stationary at level. So now let us just check for the capital. If you want to know more about unit root test, to check our channel, we have done a video on that. So now to check for the unit root of capital, you select capital. Once you click on it twice, you will have this window opened. Then you move to view, you click on view, then you move down to unit root test. Unit root test. Once you click on unit root test, we have this window. Now we have test type. We have different tests of unit roots here. You can see we have the augmented, the Kevular, the Philip-Ferron, the KPSS, the NG-Perron, and so on and so forth. So now here we are going to use ADF. The best is this trend and intercept. Then you keep this at level. Others, you just stick to the default settings here. Now once you click on OK, you have your results. You can see that the probability value of the augmented Kevular test statistics is less than 1%. So that means that this particular variable, capital, is stationary at level. So now we are assuming that all other variables are stationary at level. So we can proceed with the OLS estimation. We can proceed with OLS estimation. If you want to check for others, you just close this, then you select. Or if you want to make use of other tests, then from here you select the test you want to use and proceed with that. Now the next thing is OLS estimation. Once you have confirmed that all your variables are stationary at level, the next thing you need to do is to estimate your model. To estimate your model, you can go to quick, then from quick you click on estimate equation. Once you click on estimate equation, you will have this window. But I always prefer to highlight. So the first thing is, when you want to use this particular method, you must ensure that your dependent variable is highlighted first. So you click on the dependent variable first, press down your control, then you select the first independent variable, capital, the next independent variable, employment, the third, exchange rates. So once you have this, you right click. Once you right click, you open. Then you open as equation. Once you open as equation, you have this window. You can see all the variables are here automatically with the constants. These constants, if you like, you can erase it or delete and put it here. You will still have the same results. If you like, you can put it at the front. And if you have strong reason for estimating this particular model, without constants, then you can erase it. But here we are going to estimate with constants. So we have this. Once this is done, then you can click on OK. If you look at method, you already have the least square by method by default, and this is the sample. This is the sample 1990 to 2021. So you can get the sample size from here. You don't need to bother yourself with this option. Just maintain the default setting. So once you have the variables name listed here, then you can click OK. So here is your OLS results. If you look up, you will see dependent variable, manufacture, the natural log of manufacturing value added, MVA. What method do we use? Least square. The dates, this is the dates, and this is the time. The sample is this, and how many observations are included? We have 32 observations. Now, under variable here, we have the list of the variables. Here you will not have the dependent variable, except you are estimating with the with the lack of the dependent variable. Here we have the first independent variable, capital, the second independent variable, and the third independent variable. We have C. This C in our model is beta naught, while all these are what? Are beta 1, beta 2, and 3. You know, in our model we have two independent variables, x1, x2, but here we have three independent variables: capital, employment, and exchange rate. Now, when I was explaining the interpretation of OLS, I made mention of 3x. The first x is sign, the second x is what? Size, and the third is significance. Now, the first s, which is sign, is this minus you are seeing. This one, you know, since the relationship is positive, Eviews will not put positive in front of this value. But if it is negative, Eviews will tell you that it is negative. There are some software that will use brackets for negative. They will just brackets, they will put the value in brackets. That means it is negative. But for Eviews, if it is negative, if you will attach minus to the size. If it is positive, no sign will be attached to it, but by default, you should know that it is what? Positive. So the first x, which is sign, is this minus. So this exchange rate tells you that there is an inverse relationship between exchange rates and manufacturing value added. The second x is size, which we can also reverse to as magnitude. So now the size is this. For capital, the size is 0.678363. That's the size. For employment, 1.698617. That's the size for employment. For exchange rates, 0.245716 is the size. And for constants, 20.08752 is the size. Now the third x is significance. That significance is indicated here by probability value. Also, if you know the range, you can also make use of the T statistics. But the most easiest way to determine whether a variable is significant or not is this probability value. So now, if you look at the first variable, which is capital, you will see that we have 0.1239. This, if you multiply this by 100, it will be greater than 10%. So the implication is that the capital does not have a significant impact on manufacturing value added. In other words, there is no significant relationship between capital and manufacturing value added. But if you look at employment, you will see that we have 0.0038. This is significant at 1%. If you multiply this by 100, it will be less than 1%. So employment is significant at what percent? 1%. And if you look at exchange rate too, we have 0.0162. If you multiply this by 100, you will notice that it is what? It is also significant. You understand that? So now, for you to interpret this perfectly, you will now say that there is an insignificant positive relationship between capital and manufacturing value added. That is for capital now. Do you know the reason why we interpreted it as insignificant? It is because the probability value is what? Is greater than 5%. So since it is greater than 5%, it means that there is no significant relationship. So we can say there is an insignificant relationship between capital and manufacturing value added. Now for employment, if you notice, this is what? It is significant. So we can say that employment has a positive impact on manufacturing value added, and it is significant at 1%. Employment has a positive impact on manufacturing value added, and it is significant at 1%. Now, since all these are in percentage, we can proceed with the interpretation by saying that a 1% increase in employment will lead to 1.69% increase in manufacturing value added. This is in percentage, employment, also manufacturing value added is in percentage. So we can interpret it straightforward. A 1% increase, since it is significant, assuming it is not significant, we don't need to say a 1% increase. You don't need that. If it is not, just indicates that it is not significant. But if it is significant, you have to tell us that it is significant and also show us the increase that will occur in the dependent variable as a result of a percent increase in the independent variable. So for employment now, we can now say their employment has a significant impact on manufacturing value added as 1%. Therefore, a 1% increase in employment will lead to 1.69% increase in manufacturing value added. Now for exchange rates, this is greater than 1% but less than 5%. So we can say that there is, and take note, it also has negative sign. It has negative sign. So we can say that there is an inverse relationship between exchange rates and manufacturing value added. Or you can say that exchange rates has a negative and has a significant negative impact on manufacturing value added. At what level? At 5%. So in this case, exchange rate is significant at 5%. You can now proceed by saying that let us just interpret the relationship literally without taking or without accounting for devaluation issues. You can now say that a 1% increase in exchange rate will lead to 0.25 approximate 0.24 if you don't want to approximate percent decrease in manufacturing value added. A 1% increase in exchange rate will lead to what? A 0.24% decrease in manufacturing value added. So let me quickly write that out so that you can understand what I'm saying. For the first variable, which is capital, you can simply say that there is no significant relationship between capital and manufacturing value added in Nigeria. So you stop there. Since the relationship is not significant, you don't need to tell us that a 1% increase. No, we don't need that. But for employment, you can see that it is significant. So you cannot say that employment has a significant impact on manufacturing value added in Nigeria at what percent? At 1% level. Since it is significant, you need to proceed with your explanation. Okay, sorry, as a significant positive impact. Let's ask positive here. As a significant positive impact on manufacturing value added in Nigeria at 1% level. Or it has a significant impact on manufacturing. So now you can now say this implies that a 1% increase in what? In employment. A 1% increase in employment leads to, or will lead to how many percent increase? 1.69% increase in what? In manufacturing value added in Nigeria. In manufacturing value added in Nigeria. If you look at it now, we have considered the 3 S. The first S, which is sign, we have positive here. The second S, which is what? Size, we have it here, 1.68. 1.68. And the third, which is significant, we have it here. And at what level? 1%. So that is how to interpret your results. And for the third variable, which is exchange rates, instead of positive, you now say what? Instead of positive, it's going to be what? Negative. So this is exchange rates as a significant negative. You can change this to effect if you like. Effect. Don't forget, this is just a normal interpretation. We are not looking at the real exchange rate issue. As a significant negative effect because of this minus. That's why we included negative, this minus here. As a significant negative effect on what? On manufacturing value added in Nigeria. But at what percent? 5% level. Because this is what? Is greater than 1%. So it is at 5% level. So this implies that a 1% increase in exchange rates, a 1% increase in exchange rates, a 1% increase in exchange rates will lead to what? Will lead to 0.24 percent decrease in manufacturing value added in Nigeria. For this particular variable too, we take note of the first S, which is sign, negative, the second S, which is size, 0.24, and the third, which is significant. So this is how to interpret your OLS results. Now let us look at the other statistics here. The first one here is the R square. You can see here we have 0.618744. So you can just say that if you want to make use of R square, it simply means that the independent variable explains 62% of the variation or changes in manufacturing value added in Nigeria, while error time explain the remaining percent. In this case, we have 38% remains, right? So error time explains I explain 38% of the variation in the dependence variable. That is, which is manufacturing value added. So it is a good model, yes. But if you want to look at the real impact of the independent variable, then you need to focus on the adjusted R square. I've explained why you need to focus on the difference between adjusted R square. So here, instead of saying 62%, then we are going to be saying 58% approximately. So error time explains 32%. So that is that about adjusted R square. The next thing is the F statistics. If you look at it, is the value is 15 point something, but the probability should be the focus. If you look at the probability value of F statistics, you will notice that it is even less than 1%. So all these variables are significant. They are jointly significant in explaining what? The dependent variable. So this is also a good model. But if you look at the DW stars, you will notice that it is less than 1.55. So this is telling you that there is a problem of positive serial correlation. Please check our videos on how to perform serial correlation in Eviews. We have explained that, and one of the way you can address this particular issue is by incorporating the lack of the dependent variable in your model. Now, the information criterion, these are the information criterion. One, the archaic info, the scarce criterion, as well as the anarchin. So now if you have 2-3 models, then you have to look at these values 1, 2, 3, and don't take notes, all the values are negative, so you need to go for the one, or you need to select the one that is more negative. That's just it. So that's about ordinary least square results. Every other thing you don't really need to bother. The ones I've explained, they are the key things you need to mention in your interpretation. And don't forget, when you are interpreting OLS results, you also need to make reference to the a priori expectation, that is the theoretical prediction. If you need to look out for what theory says about the relationship between employment and manufacturing value added. If theory says that the relationship should be positive, then you can continue with your explanation by saying that the relationship or the result conforms with the a priori expectation or theoretical prediction. Then you also need to make reference to existing studies, relevant ones, those ones that have obtained or that have reported similar results or different results. If the results are similar, then you need to cite them. This particular result aligns with the work of so and so 2024 or so and so 2023 and so on and so forth. And if it contrasts, then you just need to mention in that, okay, this particular result, though it contrasts the findings of so and so, it aligns or it agrees with the result of so and so. And if there is need for you to state why it's disagree with certain studies, then you can you can raise the issue of scope, the method of analysis, the time, and some other reasons. Or maybe there are changes in economic policy after the first study has been conducted. Then you can make reference to those studies to explain why the relationship why your results is different from the previous results, or the issues, economic issues. Then you can raise those ones and to explain your results. Of course, you also need to provide more in-depth explanation of the relationship between employment and manufacturing value added. What does it say in real life, not just the interpretation? You need to identify some things that you can use to drive home your point. So now let us look at how to do the post-estimation test. I'm not going to explain that because we have covered the 4 post-estimation tests in our previous videos. So now to check for the first post-estimation test, let's say normality test, then you have to go to view, then from view you go to residual diagnostics, then you select normality. You can see this is the normality, the Jarque-Bera, the probability test results, and this one shows tells you that there is no problem of normality, that is the residual is normally distributed, because this is greater than 5%. Assuming it is less than 5%, that means there is a problem and you need to address that. Now let us look at how to do heteroscedasticity test or serial correlation. So you go to view, you select residual diagnostics, then serial correlation LM test. You click on this, then OK. Here you have your result. You can see this is 0.00, which is significant, and it's not supposed to be. That means this particular model has issue. So you must correct this results. Then once you correct the results, you have to re-estimate again. For instance, if you incorporate the lag of the dependent variable, then you first report that okay, this is the problem on ground. Then when you correct, what is your result? You have to present your results. So that is how to address serial correlation issue. You just go to estimate, then you incorporate the lag of the dependent variable, which is ln of MV. Then you estimate again. This one also we have addressed it in one of our videos. Please just check our channel for videos on how to perform serial correlation in Eviews. You will see the procedures there. The next thing is heteroscedasticity test. Then you go to Eviews again. You go to views again. Then from views you move down to residual diagnostics. Then from residual diagnostics you select heteroscedasticity test. Once you select it, click on it, you have this. We have different tests. So the one that I'm going to use there is this Breusch-Pagan-Godfrey. So you just click on OK, then you have your results. The probability of F statistics is greater than 5%. So this means that there is no problem of heteroscedasticity in this particular model. The last test is the Ramsey reset test. To do that, you go back to view. Then from view, you select stability diagnostics. Next is Ramsey reset test. Once you click on it, the number of fitted times, maintain that one. You click OK, then you have your result. The probability of F statistics here too is less than 5%. That means there is a problem with this particular test. So you must take steps to address it before presenting and discussing your results. If you don't address it, you will have your results will not be suitable for policy formulation. So with this, we have come to the end of this particular video on how to estimate ordinary least square regression from A to Z. Please, for videos on the pre-test as well as post-test, kindly check the description of this particular video. You will see links to all the post-tests that we have done previously. You just need to click on it, it will take you there, then you watch that particular video and later you come back to this one. So with this, I'm very sure that you will not have any problem with your analysis, particularly when you are using ordinary least square regression method. One thing that is very important is that all your variables must be stationary at level. So if all your variables are stationary at levels, then there is no one that can dispute your results. So I want to use this opportunity again to plead with you that if you are just coming across our channel for the first time, kindly subscribe to our channels to be part of this great community. I'm telling you, you will never regret it. And also to all our existing subscribers, please continue to share our videos. We really appreciate you. We know what you are doing for us. We can see the results. Thank you very much.